So we're going to look at this question, which is taken from the February-March DBE exam, national exam, 2011. So they tell you, fertilizer company produces ammonia on a large scale at a temperature of 450 degrees. So we have a temperature. The balanced equation below represents the reaction that takes place in a sealed container, which they give to us, and of course they tell us that delta H is less than 0, so the forward reaction is exothermic. To meet an increased demand for fertilizers, the management of the company instructs the engineer to make the necessary adjustments to increase the yield of ammonia. So we've got to do things to make sure that we favor the forward reaction and we get more ammonia when equilibrium is reached. In a trial run on a small scale, the engineer makes adjustments to temperature, pressure, and concentration of the equilibrium mixture. The graphs below represent the results. So when we look at the graph, and it's a black and white graph, so let's use colors to track what's happening with everything. Here we have the nitrogen. It goes along, then at T1 for some reason it spikes, probably because we put it in. Then it gets smaller again and spikes again, and then I use it up, and then there's a nice little gentle change. Alright, so that's for the nitrogen. We do the same with the hydrogen. Here we go. It doesn't spike, but it gets less. So now I know I'm favoring the forward reaction. It also spikes a little bit at T2, then it starts to get used up, and then we increase it a little bit. Okay, now if we do the same for ammonia, so there we go. Ooh, doesn't spike, but gets more, so I favored making it. It also spikes, then we favor making it, and then it gets lower. So there's three things that we're looking at: temperature, pressure, and concentration. Over here in T1, the only thing that changed like instantly was N2. So over here, I increased the N2 concentration. Okay, that's what I changed. Then, okay, we look at this one, and it's an instantaneous change in concentration of everything. Okay, we're working with gases, and if we look at it, we then favored the forward reaction. And remember, I've got to choose between temperature, pressure, and concentration. Temperature doesn't make an instantaneous change like this. So now my option is pressure, and I look and I go, well, I've got 4 particles on the left, 2 on the right, okay, which means whatever I did at T2, I favored the forward reaction because I made more NH3. That tells me that I must have increased the pressure. I've increased the concentration of everything because I made the volume smaller. By increasing the pressure, though, I did favor the forward reaction. Then, the last option, obviously now, is going to be temperature. But, what happens here? When I changed the temperature, okay, and I look at this and I go, well, I got more reactant at the end and I used a product, so this has to be the temperature change. Alright, because of the 3 things we changed, this is the last one, has to be the temperature. And then we'll deal with it later. So, first of all, identify the changes made to the equilibrium mixture at each of the following times. You've got to be specific, so you can't just say pressure was changed, concentration was changed, etc. Now, we agreed, well, I told you, that at T1, the concentration of the N2 was increased. Okay, so we agreed with that. Then at T2, the pressure was increased. Okay. Great. At T3, now we've got to say, well, which reaction was favored? And because I made reactants. I got more reactants at the end, and it's an exothermic reaction. It means I favored the reverse reaction, and the reverse reaction is endothermic. That means I favored the reverse reaction, and the only way I can favor the reverse reaction is if I increased the temperature. Okay. So, there we go. Alright. At which of the above times did the change to the reaction mixture lead to a higher yield of ammonia? Well, if we look at it, and now we've got to look at how many times the ammonia went up, and that's the yellow one. So over here, it went up. Over there, it went up. Over here, it went down. So in other words, at T1 and T2, I increased the yield. Great. So T1, whoops, not I, T1 and T2. Perfect. Now we get to the questions we really like, right? The engineer now injects 5 moles of ammonia and 5 moles of hydrogen, right, into a 5 decimeter cubed container. The equilibrium is reached at 450 degrees. Upon analysis, he finds that the mass of NH3 is 240 grams. Calculate the equilibrium constant. First of all, before you do anything else, we can't work with grams. Up until now, you might have only seen questions where we have number of moles of concentration. So the very first thing I'm going to need to do is make the ammonia into number of moles. Okay? Otherwise, I can't do my calculation. So, I want the number of moles of ammonia, and we know it's mass over molar mass, 20,4. Nitrogen's mass is 14. Hydrogen is 3. So I have 20,4 divided by 17, which gives me 1,2 moles. That's at equilibrium. I have before conditions and I have after conditions. I know I'm going to need a table. Okay? So, let's set up our table. Ooh. So, here we go. It's going to be a bit of a messy table, but you'll be fine. So we have the same lines all the time, all the way down. Okay, so we have the ratio line, initial, change, equilibrium, equilibrium. And I have, there we go. It's not the neatest, but you'll get it. So we put our ratio, initial number of moles, change, which is also in moles. Then we have our equilibrium number of moles, and we have our equilibrium concentration, okay, which is moles per decimeter cubed. And I need to remind myself that this is actually, and I'm going to put it here so I don't forget, that the volume is 5 decimeters cubed. Alright, so I have ammonia, I have hydrogen, and I have NH3. In the question, I was told that I have 5 moles, and we've just worked out that we have 1,2 moles. Oh, wrong place. That I have 1,2 moles there. Now I need to put in the ratio, and that's from the balanced equation, which is 1 to 3, 1 to 3 to 2. Alright? I don't have any ammonia to start off with, which means I had to add in 1,2. Remember, now we've got to do the sorry about that. I'm going to go back here and hopefully I can... Give me a second. Alright, so we need to times by 1 to over God. So we're going to take 1, 2 times by 1, divide by 2, and then we put the answer over here, which means this is 0.6. Then we've got to take 1, 2 times by 3, divide by 2, put it over here, so that gives me 1.8. Alright, I had 5 moles, I use 0.4, so now I have 4.4 moles here. Okay, I had 1.8, I had 5, used 1.8, so now I've got 3.2. But to get my concentrations, I need to divide by 5. Okay, I need to divide by 5. That's very important here. So I'm going to divide by 5. So I'm going to go 4.4 divided by 5, and this gives me 0.88. 3.2 divided by 5, which now gives me 0.64. 1.2 divided by 5, which gives me 0.24. Please don't forget to divide by the volume, otherwise it's not going to work. I've got my equilibrium concentration, so now I can say my Kc value is NH3 squared over N2 times H2 cubed, so 0.24 squared divided by 0.88 times 0.64 cubed, and of course you put that in your calculator, okay, and what that gets us is 0.25, has no units, and we're done. So it's just taking this one step at a time. Hope that helps.